Today we are going to introduce differential equations and talk about slope fields. Differential equation is an equation where we have equation involving a specific function and its derivative. Here's an example: y double prime minus y prime minus 6y equal to 0. It's a differential equation because here dependent variable is y and it involves the derivatives of y. Another example: dx over dt is equal to x squared t, where x is a function of t. That is also an example of differential equation. There's many kinds of differential equations, but in this course we are only going to discuss two. First order linear differential equations, we'll talk about these in the next video. And the second type is separable differential equation. First order linear are the ones that can be put in the form y prime plus p of x times y is equal to q of x. So dy dx plus a function of x times y equal to a function of x. Separable equations, just like the name suggests, separable equations are the ones where we can separate the equations. X's can be separated to one side and the y's can be separated to the other side. Separable equations are generally listed in the form dy dx is equal to f of x times g of y. So we can easily isolate the y's on one side and x's on the other side, and then we can go ahead and integrate to find the solution. In Calc 1, we talked about if we have a given function y, we can go ahead and find the derivative by doing the differentiation. Now we're going to be going backwards. We would be integrating dy dx to get back to y. So we're finding the original function whose derivative is given to us in terms of differential equation. Let's talk about the degree and order of a differential equation. What's the difference between degree and order of a differential equation? Keep in mind the order is the highest derivative that appears in your equation. Order is the highest derivative that appears. So if your equation has a second derivative, third derivative, fourth derivative, that would be the order. And degree is what power is the highest derivative raised to. That is the degree of the differential equation. So here's two examples. Number one, what's the degree and what's the order? Degree, let's first talk about the order. What is the highest derivative that appears over here? The derivative is third, so that's going to be the third order. And what power is that derivative raised to? It is raised to the power 1, so degree will be 1. Next, what is the order and what is the degree? Order is what is the highest derivative that appears in here. The highest derivative that appears here is dy dx. That's the first derivative. So that would be the order. And the degree in this case is what exponent is that highest derivative raised to. That would be 4. That's the degree in this case. This video's focus is separable differential equations. We will see a lot of separable differential equations. We'll look at general solutions and some particular solutions. So let's go ahead and identify a few equations are given. We're just trying to see if they're separable or not. So dy dx is equal to y sine x. We can go ahead and divide with y, and then we'll have y terms on one side, x terms on the other side. So that would be separable. Next one, y dy is equal to x dx. Yes, separable. Next one, we can bring the function of y down, and the right hand side would be just the functions of x. So yes, separable. This one is also separable. We can take dt to the other side and then integrate. Next, we have dy over dr is equal to negative y over 3. We can write it as dy over y is equal to negative 1/3 dr. So that is separable. That would be yes again. This is also separable. We can isolate the x's on one side and y's on one side. We can write it as 1 over y dy is equal to 1 over 3 plus x dx. That is separable. Let's check out number 7. Is that separable or not? Looks like it is separable because we can write it as dy dx is equal to x over x plus 2 times y. And next we can divide with the y and x over x plus 2 dx. And then go ahead and integrate. That would be separable. Yes again. Let's check out number 8. Does that look like separable? Is there any way I can isolate the x's on one side and y's on the other side? No, that's not going to be possible here. So that is not a separable differential equation because there's no way I can isolate all the y terms on one side and x terms on the other side. Let's check out some examples of solving the separable differential equations. In this video, we're only going to look at separable differential equations. Dx minus e to the power 3x dy is equal to 0. So let's go ahead and put it in the nicer form here. Now, I'm going to go ahead and divide both sides with 1 over e to the power negative 3x. 1 over e to the power negative 3x dx is equal to dy, which turns out to be e to the power negative 3x dx is equal to dy. Let's go ahead and integrate. Now, differential equations will have many possible solutions. Just like when we did the integration, we know there was a constant c. When we are given a function, when we find its derivative, there's many possible functions whose derivative can be, for example, if the derivative is 2x to the third, what is the function whose derivative is 2x to the third? What function would have the derivative 2x to the third? That would be 2x to the fourth over 4, which is going to be x to the fourth over 2. So if we do the derivative of x to the fourth over 2, the derivative would be 2x to the third. What if we did the derivative of x to the fourth over 2 plus 5? It would be still the same. What if we did the derivative of, it would still be same. What if we did the derivative of this function? It would still be same. So there's many possible functions who has the same derivative. So when we are given the derivative, we're going back to the function. There's many possible functions. They all are going to be parallel to each other, and they have the same derivative. So when we find the solution here, when we're going to integrate, we would be adding a constant, arbitrary constant c. All right, I made a minor mistake here. This is not going to be e to the power negative 3x. This is going to be e to the power 3x because I took it to the numerator. Oh, this was a positive. Okay. We're back. This was not negative. Now it will become negative. All right. What is the integral of e to the power negative 3x? Well, integral of e to the power negative 3x is e to the power negative 3x over 3 plus c is equal to y, and that's our general solution. It does have an arbitrary constant c, which can take on any value, the constant c, depending on which particular solution you're looking for. Check out another example. Dy dx is equal to y plus 1 over x. Dy over y plus 1 is equal to 1 over x dx. Go ahead and integrate. We have the derivative of denominator sitting in the numerator. So left hand side, it would be natural log of y plus 1, natural log of x plus a c. Now, if you want, we can go ahead and do a little simplification here. Natural log of y plus 1 is natural log of x times c, because we can write c, we can think of c as a constant, we can think of c as natural log of c. So natural log of x plus natural log of c can be written as natural log of x times c. So we can say y plus 1 would be, because we have the absolute values, would be equal to plus minus xc, or we can say y is equal to plus minus xc minus 1. Y is equal to plus minus cx minus 1 or xc minus 1, however you want to think of it. Next example, dy over dx minus 3y is equal to 5. Again, it's a differential equation. Dy over dx is equal to 3y, 5 plus 3y. Let's leave it as, I was planning to bring the 5 to the left hand side, but I will just leave it like that. 5 plus 3y. Now, this is going to be, how can I isolate? So we can bring 5 plus 3y on the left hand side. Dy over 5 plus 3y, 5 plus 3y is equal to dx. Yep, that looks good. Now we can go ahead and do the integration here. Now, in order for me to use the natural log, I need to have derivative of denominator sitting on the top. Derivative of 5 plus 3y with respect to y is going to be 3. So I'm multiplying, dividing with a 3 here to make up for that. And to make my life easy, I don't have to worry about, let's see. So I'm just going to say y is greater than 0, then I don't have to worry about absolute value sign to make up for the domain of natural log of function. So here that is going to be 1/3 natural log of 5 plus 3y is equal to x plus c. And this is, we can leave our solution in this form, or we can go ahead and further simplify more. It's okay to leave it in this form. This is not represented. We don't have y explicitly here. We have y written implicitly. But if you want to go ahead and isolate the y, we can go ahead and do 5 plus 3y natural log is equal to 3x plus c, because c times 3 would be still a c. Now we can raise both sides to the power e, and that's going to leave me with 5 plus 3y. I don't have to worry about absolute value bars because I did say y is greater than 0. 5 plus 3y is equal to e to the power 3x times e to the power c. E to the power c, because e is a constant, e to the power c will be also a constant. I can write it as 5 plus 3y is equal to constant a, e to the power 3x. We can represent e to the power c as a constant a, or b, or d, whatever constant you like. Now from here, it's easier to isolate the y. 3y is equal to a e to the power 3x minus 5. Y is equal to a e to the power 3x minus 5. And I'm not dividing this with the 3 because a over 3 will be still a constant. So you can just leave it as a constant a. There's no need to write a 3 here. All right, so that is our general solution, and the constant a can take many shapes and forms. Check out more examples. I'm going to make some room to do the next example. We are solving differential equations, only separable ones in this video. Sometimes you will have to do a little bit of work to separate the differential equations. So here I have 4y plus yx squared dy is equal to 2x plus xy squared dx. Okay, so y, I can pull out 4 plus x squared dy is equal to, I can pull out the x, 2 plus y squared dx. Now it is time to isolate the variables. So y over 2 plus y squared dy is equal to x over 4 plus x squared dx. Go ahead and integrate both sides. So this is going to leave me with natural log of, I can do the u substitution here because the derivative of denominator is sitting in the numerator. But in order for me to use a u substitution, you can go ahead and write this separately on a different piece of paper and go ahead and evaluate this. But I already know that in order for me to use the natural log of u to call my denominator u, I need to have the derivative of denominator sitting in the numerator. So I'm going to multiply numerator and denominator with a 2. And same thing here, I'm going to multiply numerator and denominator with a 2. Turns out to be 1/2 natural log of 2 plus y squared. No need to put the absolute value bars because 2 plus y squared is always positive. Natural log of 2 plus y squared is equal to 1/2 natural log of 4 plus x squared plus a c. Okay, now what can we do? We can multiply everything with a 2 to make our life easy. Natural log of 2 plus y squared is equal to natural log of 4 plus x squared plus a c. C times 2 is still a constant, so I'm just going to leave it as a constant. Now we can raise both sides to the power e because we don't want to have natural logs there. Turns out to be 2 plus y squared is equal to 2 plus y squared is equal to e to the power, let me rewrite it here. So this would be e to the power natural log of 4 plus x squared times e to the power c. E to the power c is a constant, so 2 plus y squared is equal to 4 plus x squared times a constant, which is c. So we can say 2 plus y squared. We can distribute the c inside. 4 times c is still a c. And finally, y squared is c plus cx squared minus 2. C minus 2 is still a constant. Y squared is equal to cx squared plus a c. And that's going to be my equation. If you want to get y by itself, y is equal to plus minus square root of cx squared plus a c. And that's our solution in this case. More examples. Let's see. Let's go ahead and check out number 6. So for number 6, again, my goal is to try to isolate the variables here. I'm going to try to get the y terms on one side. Dy over y is equal to x squared over 1 plus x to the third dx. Time to integrate. Natural log of y is equal to, we can do the u substitution here. On the right hand side, we can do the u substitution. We can let 1 plus x to the third as a u, but in order for me to use a u substitution or natural log of u, I would need the derivative of, let me rewrite this got a little messy, 1/3. Okay, so 3x squared, the derivative of denominator is sitting in the numerator, so that's going to be 1/3 natural log of 1 plus x to the third. And I do need the absolute value bars here because I have 1 plus x to the third, which can be negative. plus a c. So natural log of y is equal to 1/3 natural log of 1 plus x to the third plus a c. We can multiply everything with a 3 here if we want. dy. Oh, go back. That's not right. This wouldn't be dy over y. This is going to be y dy. Okay, that was not nice. There we go. When we separate the variables, it's going to be y dy is equal to x squared over 1 plus x to the third dx. Now I need to multiply and divide with the 3 to get the common denominator. Turns out to be y squared over 2 is equal to 1/3 natural log of 1 plus x to the third plus a c. Let's multiply everything with a 2. Turns out to be 2/3 natural log of 1 plus x to the third plus a c. Now we want to isolate the y here, so I can go ahead and do the square root, which is plus minus square root of 2/3 natural log of 1 plus x to the third plus a c. All right, next example, we will look at number 7. We have cosecant y dx plus secant x dy. Let's go ahead and isolate the variable. That would be negative cosecant x, negative cosecant y dx is equal to secant x dy. We can go ahead and separate them now. So I can say 1 over secant x dx is equal to negative 1 over cosecant y dy. And 1 over secant x is cos x dx. And negative 1 over cosecant y is sine y dy. And it's going to be negative. Now, what is the integral of cos x? Integral of cosine x is sine x. Integral of cosine x is sine x plus c. And integral of negative sine y would be cosine y. Cosine y. Now, if we want to get the y by itself, we can say y is equal to cosine inverse of sine x plus a c. Okay. All the solutions we saw so far, they did have a constant c in there. Now, all these were the general solutions of the differential equation. Now, we're going to look at the particular specific solutions passing through a particular point. Such equations are also referred as initial value problems. We saw them in Calculus 1. We didn't call them differential equations. We call them initial value problems. In these kind of problems, we are given an initial condition. So, once we find the general solution, we would be using this initial condition to find that specific solution passing through the point when x is 0 and y is 1. So we are looking for the solution. Differential equations have many possible solutions. We're looking for the solution that passes through the point 0 and 1. X is 0, y is 1. Okay. Y, I can go ahead and isolate the variables right away. Y dy is equal to dx. Turns out to be y squared over 2 is equal to x plus c. Now I'm going to plug in the values to find out the value of c. So I'm going to replace x by 0, y by 1, 1/2 is equal to 0 plus c. This gives me c is equal to 1. So my particular solution will be y squared over 2 is equal to x plus 1/2. I could isolate the y by itself over here if I wanted to. I'm going to leave it in this form. If you are being asked to write your solution in the explicit form, then you do need to isolate the y. Next, we can factor out a y from the right hand side. Now isolate the variables. Dy over y is 1 plus x squared dx. Time to integrate. Natural log of y is equal to, how do we integrate 1 plus x squared? That would be x plus x to the third over 3 plus a c, right? Okay, now I'm going to go ahead and find out let's isolate the y here before we plug in the values. Natural log of, so we will raise both sides to the power e, raised to power e. This will leave me with e to the power natural log of y is equal to e to the power x plus x to the third over 3 plus c. Now e to the power c can be written as a constant. So y is equal to x plus, not x actually, e raised to that power. E raised to the power x plus x cubed over 3. And we can write the constant e to the power c will be, well, let me actually expand this. That might make more sense, because e to the power natural log of y would be just y, or absolute value of y. I'm dealing with positive values here, so I'm not going to worry about the absolute value. This can be written as e to the power x plus x to the third over 3 times e to the power c. E to the power c is what I'm going to call a constant a or b or c, whatever you want. All right, now it's time to plug in our initial condition. We're given that when x is 0, y is equal to, when x is 0, y is 5. So I'm going to go ahead and plug in this initial condition. When x is 0, y is 5. 5 is equal to a, e to the power 0. So 5 is equal to a. My constant turns out to be 5. My specific solution is y is equal to 5, e to the power x plus x cubed over 3. Okay, y is equal to 5 e to the power x plus x cubed over 3. That looks good, and that is my particular solution passing through this point. dy dx is equal to x to the power negative 3. Y is 3 when x is 1. Okay, same procedure. dy is equal to x to the power negative 3 dx. Time to integrate. Y is equal to x to the power negative 2 divided by negative 2 plus c. Y is already by itself. So this is my general solution. And now I can find the particular solution by replacing the x by 1 and y by 3. X is 1. That's going to be negative 1/2. And then 1 over 1 to the power 2 plus c. Okay, so 3 is equal to negative 1/2 plus c. 3 plus half is equal to c. And 3 plus half is 7/2 is equal to c. So a particular solution in this case, particular solution is y is equal to negative 1 over 2x squared plus 7 over 2. This is the solution that passes through the given point. Let's check out one more example, number 10. Here again, we do have a separable differential equation. I'm going to separate the variables. dy square root of y dy is equal to square root of x dx. Time to integrate. What is the integral of square root of y? That's going to be 2/3 y to the power 3/2, 2/3 x to the power 3/2 plus a c. Now we're going to plug plug y as 4 when x is 1. Y is 4 when x is 1. Okay, almost there. Square root of 4 is 2. 2 to the third power is 8. 8 times 2 is 16 over 3 is equal to 2/3 plus c. C comes out to be 16 over 3 minus 2/3, which is 14 over 3. That's my constant here, 14 over 3. Y is 4 when x is 1. Square root of 4 is 2. 2 to the third power is 8. 8 times 2 is 16 over 3 is equal to 2/3. Yep, that is correct, 14 over 3. All right, so my particular solution will be, I'm going to replace the c by 14 over 3. And that is our particular solution. That's what we were looking for, this equation. We have several more examples. The next one, again, it's a differential equation, but my independent variable here is t and dependent variable is, I'm not going to complete at this point. We can go ahead and integrate, and this is going to be u to the power negative 3 plus 1 divided by negative 3 plus 1 is equal to t to the power 4 over 4 minus t squared over 2 plus c, and then plug u as 4 when t is 0 and find out the particular solution. Next kind of example, we're looking for if this given y value is a solution to the given differential equation. Differential equation is 2xy prime, which is 2x dy over dx plus 4y is equal to 3. So first step, I'm going to, y is 1 plus x to the power negative 2. If I do the derivative, dy dx is going to be, derivative of 1 is 0, negative 2x to the power negative 3.
Now let's go ahead and replace dy dx by what value we just find and y by what is given, and see if my left hand side come out to be equal to right hand side. So I'm just going to work on left hand side right now. Left hand side, 2x times dy dx, which is negative 2x to the power negative 3, plus 4 times y is 1, plus 1 over x squared. And now we're trying to see if this is a solution or not for the given differential equation. So I just need to make sure that my left hand side does turn out to be equal to 3. If it does, then I do have a solution. If it does not, then I would say nope, that is not. Is that equal to 3? Negative 4 x to the power negative 3 plus 1 is negative 2, plus 4 plus 4x to the power negative 2. Is that equal to 3? Does not look like to me. These are going to cancel. 4 is not equal to 3. So that means this is not a, no, this is not a solution. Find all values of e to the power ax such that y is equal to e to the power ax is a solution to this differential equation. Okay, so y is e to the power ax. Y prime would be e to the power ax times a, and y double prime would be a square e to the power ax. And we want to find out the a that will satisfy the given differential equation. So I'm going to replace these values in the differential equation and solve. Y double prime is a square e to the power ax plus 4 times a e to the power ax minus 12 times y, which is e to the power ax is equal to 0. So we can pull out e to the power ax. E to the power ax inside is a square plus 4a minus 12 equal to 0. Now e to the power ax is never 0. Exponential functions are never take on the y value 0, because the y is equal to 0 is the horizontal asymptote for exponential functions. This e to the power ax is never equal to 0, so that means a squared plus 4a minus 12 is 0. And factor, no, that doesn't look right. Let's see. E squared plus 4a minus 12, the factors would be 6 and negative 2. That is correct. That is correct. So a would be positive 2 and negative 6. These are the two solutions. These are the two solutions. Okay. Dy dt is e to the power t sine. These are your try me problem. Pause for 5 minutes, try these problems, and come back and check. Y, we are going to isolate the variable. Dy would be equal to e to the power t sine of e to the power t minus 2 d2. And we're given the initial condition. Let's go ahead and do the derivative on both sides. The right hand side, e to the power t sine of e to the power t minus 2 dt. I'm going to do the u substitution because I will let e to the power t minus 2 as u, e to the power dt will be du. And this integral turns out to be a u integral sine of u du. What is the integral of sine of u? That would be negative cosine of u. And I'm going to replace u by what we called it in the beginning. Cosine of e to the power t minus 2 plus a c. And this is my general solution, but we were looking for a particular solution. So to find the particular solution, I would just have to go ahead and plug in x as natural log of 2 and y as 0, because that's the initial condition given to me. So y is 0, x or t, not x here in this case, this is a t. So t is natural log of 2 and y is 0. Negative cosine e to natural log of 2 minus 2 plus a c. E to the power natural log of 2 is going to equal to negative cosine of 2 minus 2 plus c. Turns out to be 0. Negative cosine of 0 plus c. Cosine of 0 is equal to 1. So c turns out to be 1 in this case. My constant particular solution, the constant c will be 1. So our final answer here would be y is equal to negative cosine e to the power t minus 2 plus a 1. This is the particular solution passing through the given point. Don't be scared when you look at a point like y natural log of 2 is equal to 0. Natural log of 2 is a constant. If you go ahead and grab your calculator, natural log of 2 is 0.6931. So you're looking for 0.6931 and 0. Which solution curve passes through 0.6931? That's all we were going to discuss. And we only looked at the separable differential equations in this case.